Okay, welcome everybody to the HAO colloquium today. Our today's speaker is Yuta Notsu. It is my great pleasure to introduce Yuta. Yuta Notsu got his PhD in March 2019 at Kyoto University in Japan in the solar physics group there, supervised by Professor Kazunari Shibata. After that, he first came to Laboratory for Atmospheric and Space Physics, LASP, University of Colorado Boulder, with JSPS Research Fellowship in 2019, and then transitioned to postdoc and currently research scientist at the same institution. He is mainly studying stellar magnetic activities, especially superflares and potential stellar CMEs on solar type G-type stars and cooler KM-type stars, using the various photometric and spectroscopic data from space and ground-based ground telescopes. Through these observational studies, he investigates how frequently superflares occur on GKM-type stars, how large superflares and CMEs occur in the stellar atmosphere, and how are affected from these flares. Recently, he also joined MAVEN EUV team to apply his young son's studies to early solar system evolutions. So today, Yuta will be speaking on recent spectroscopic observations of stellar flares and possible stellar mass ejections.
Okay, thank you for the introduction, and thank you for the invitation for the talk. Maybe 20 people here, so it's a great pleasure. And today I will talk about recent spectroscopy observations, stellar flares. Maybe you can hear me, right? Maybe okay. Yeah. If you cannot hear me, please let us know. Recent spectroscopy observations, stellar flares, and possible stellar mass ejections, and with many collaborators. And if you have any maybe quick questions, please interrupt anytime. Maybe longer questions we can discuss after the talk. And I assume most of the people are solar. Yeah, Jeff is stellar experts, but there are some stellar experts. But I think most of the people is solar people, right? So if I say something like unfamiliar term, please let me know, and then I explain. Okay, and before going into detail, I just briefly introduce. Yeah, I think I met most of you, but yeah, just briefly introduce. And I got PhD in 2019 Kyoto with Shibata-san there. And since after that, I moved here first as some Japanese fellowship position, and now a research scientist at last. And also, I'm in NSO, so few blocks away from here. So yeah, anytime we can discuss. And I'll be again here at Boulder Solar Day in a few weeks. And my topic is multi-wavelength observation. And my current research topic is mostly on multi-wavelength observation, stellar flares and CMEs, and trying to promote more solar stellar connections. And for example, I think some of you attended some NSO Solar Focus meeting in February. Yeah. And also, recently I tried to join more and work with more on stellar UV observations and also UV instrument plans in LASP for future astrophysics observations. Oh yeah, and I came from Kyoto. So if you have any questions about Kyoto or Japan, and if you have any conference in Japan, please ask me, and I can answer any travel options, like what you should visit, for example. And today's topic is stellar, and I assume many of you are solar topics, but actually there are, there's one textbook.
Can I just comment?
Yeah, go ahead.
I just finished writing the update on the book, Cold Stars and the Effects on Exoplanet Atmospheres. So it's a second edition, which is now at the publisher and hopefully will come out in the end of the year.
Okay, published in end of
This is 2019. The new book hopefully will come out at the end of 2024. And it'll be an update because a lot has happened in the last 5 years.
Yes, last 5 years, a very interesting phase. And I'm happy to read it. And maybe all of you must read it. And there are some other review papers, for example, by Adam Kowalski in Living Review Solar Physics, or another Living Review Solar Physics in Clyber, and also I accepted to write another stellar stream review recently, so I have to write in 1 or 2 years. But yeah, there are some, and there are the other two I joined, but there is for example, there is a space science review by our EC team on extreme solar events. So you have any, I can, if you need it, I can send a link, and yeah, or you can, I think you can find a recording of the talk. Okay, so let's go into detail. So I think I don't have to include my this page, but solar flares. These are large eruptive events in solar atmosphere, and these are triggered by magnetic reconnection. In recent, it is understood now, and that for some sense. and the important point is observed in various wavelengths, and I think it's same for most of the things understood for solar flares. We try to apply to stellar flares. And the important point is observed in various wavelengths. And if you, for example, even these are examples of EUV wavelengths, Wi-Fi UV wavelengths, but as you can easily realize, and the structure is very different. And these are all from same flares from SDO, but structures are different. Actually, these difference of the different wavelengths observation gave us a view of the, for example, standard model of solar flares, and the magnetic reconnection occur in corona. And one thing is energy is transporting in some ways into the, for example, particle acceleration into a lower atmosphere, then energy is released. Of course, more details you can hear solar flare talk in this seminar series. And in addition, we have mass ejections, and that will be a most important topic of the latter part of my talk. Yeah. So in the case of solar flares, I think there are many space weather, as you know, there are many space weather topics. And large solar flares can have a severe impact on our Earth and society. And for example, among them, several large severe events have been detected in recent 100 to 200 years. One great example is the Carrington event, occurred in 1859, 165 years ago. 165 years ago. 3 days later. Yeah. September 1st. And this was actually this was the first and largest flare we recorded. And yeah, recently there are some discussion how large the event was in terms of X-ray based on the
Could I just add to that? I did an estimate of flare. I think it was on AB Leo.
Mhm.
It was X 600,000.
Mhm.
That's the estimate.
Yes, super flares. Yes. So this X is a solar flare X-ray scaling, and we can apply to super flares. Yes. And so usually these flares larger than that value is called super flares. But this Carrington event is maybe one biggest one, and based on 200-year observation, no 165-year observation, but we don't know larger flare occur on Sun or not. Because observation limited. And in terms of frequency, occurrence frequency observation solar flares, we already know based on 160-year observation, we know the power distribution like this. So from nanoflare regime to normal solar flare regime up to Carrington event. But a largest flare, total energy in integrating all radiation from optical to X-ray, and total energy is a few times 10 to 32, and the frequency is runs in 10 or 100 years order of 100 years. But we don't know much larger flare occur on Sun or not. But because we didn't know, only with modern solar flare observations, just 160 years. So we don't know how much larger flare occur or not, because the frequency and observation length is limited. So that's why we did a stellar observation, because there are plenty of stars similar to the Sun. So if we, for example, if we observe the one Sun, so observing one Sun, of course we have a one Sun, one Sun for 10,000 years, roughly corresponding to observing 10,000 Sun-like stars for 1 year. And about 15 years ago, 15 years ago, the space telescope called Kepler was launched in 2009, March, I as well remember. And that observed a lot number of stellar brightness of number of stars, more than 10,000 stars. Actually up around 90,000 stars. So then we analyzed in early 2010s, when I was undergrad, actually in Kyoto University, we started a project to search for stellar flares using Kepler data. Kepler is well known for exoplanet survey telescope, so observing a stellar light for many stars for years and years, like for up 4 years. And this is an example of the light curve show of slightly younger than the sun, by the way, and with some flares. This is a stellar brightness changes. Actually, stellar brightness is still changing, but because of rotation, I explain a bit later. But there are certain brightenings here or here or here. So, and if we enlarge the light and enlarge the light curve, there are certain brightenings and a slightly gradual decay. And after some careful inspection of the all events, and this corresponding to sudden brightness increase caused by stellar flares. And actually, the amplitude.
Could I ask the number 10 to 33 to 36 Hertz? Is that in the bandpass of Kepler, or is that an estimate of total electromagnetic spectrum?
Whole electromagnetic spectrum, assuming some flare temperature. So assuming 10,000
like 10,000 degrees.
10,000 Kelvin black body. For this case, yes. Actually, there is some discussions in a flare temperature, but roughly speaking, in stellar white light flares are caused by chromosphere optical tick or upper photosphere optical tick. So the temperature is around 10 to 9,000 or 10,000 is a good proxy. There are still some discussions. That's a recent topic, but for this study, we assume the Kepler is a bandpass from 4,000 to 9,000 angstrom, but we assume the whole temperature or black body temperature to convert to electromagnetic energy. Anyway, so flares here, and also the stellar brightness itself showing some quasi-periodic brightness modulation. Actually, almost all of the superflare stars having this shape is a bit different depending on stars, but some quasi-periodic brightness changes, and there are some amplitude. And these are corresponding to existing large star spot, because if the star spot, of course, locating various longitude, by the way, but if the star spot is on some side of the star and it rotates, the brightness can change. So these brightness changes showing the existence of large star spot. Actually, the amplitude is much larger than the brightness variations from the sunspot, so it's much larger. And also, free amplitude is much larger than optical solar flare, white light flare on the sun. So then flares are much larger. Okay, Kepler reviewed the young and old solar type stars, even younger stars, of course younger stars, but the older sun-like stars have super flares, and the super flare stars showing quasi-periodic brightness modulation, and these roughly corresponding exist in large star spots. And thanks to number, we detected like more than 1,000 events on a few hundred stars, so we can discuss how flare activity has changed over stellar age. So flare activities depend on stellar age. Stellar age, why we know stellar age? This depends on actually just use the rotation period, because the star was born with very fast rotation. But as the star become older, the star lose angular momentum. Actually, our sun still lose angular momentum every day because of the solar wind and the CMEs both. But young rapidly rotating stars, and the star was born with a much young rapid rotation, but gradually decrease. So if we see, then we plot the flare frequency for rapidly rotating star and also the slowly rotating star like the sun. The sun has 25-day rotation period on the current age. So frequency distribution like this. So we can see power distribution, but the exact value of the frequency is very different. So the frequency distribution gradually decrease as a function of rotation period. But still, so younger rapidly rotating stars, more frequent, more energetic flares. Please remember, I explain youngsters also in a later presentation, but a later part of my presentation, but more frequent, more energetic flares. But some like slowly rotating stars still have super flares with 10 to the 34 L. So you might remember Carrington event is a few times 10 to 32 L, X80, X50, X80. But it's like 50 or 100 times larger than the largest solar flares in 100 to 100 years. So still they have a super flares. And we can compare with the solar flare frequency. I already showed the solar flare frequency like this, but we can plot the stellar the distribution from Kepler like this. And super flares whose energy is around X700 or X1000 can occur on sunlight stars once every 1,000 or 3,000 or 6,000 years, respectively, like this. So this is a result from Kepler, so based on sunlight star observation. But this is from stellar data, and there's 1,000 years only from stellar data. So there's a question happened. Maybe all of you, or most of you have a question. Is there any record on our Earth? Because our Earth has some history of course, if superflare can happen with this frequency, are there any records here? The answer is yes and no. And yeah, still we under investigate. But actually, there is a very interesting topic. Oh, sorry, in the movie. So actually, it's a very hot topic from same year, 2012, when the first Kepler superflare was discovered on the same year. Actually, 1 week difference with the Nature paper, 1 or 2 weeks difference, by the way. So there are some investigation to detect extreme solar events with the isotope measurements of tree rings and ice core. In the right upper panel, this is the example. Originally, this carbon-14 is isotope. You know, carbon is 12 is the normal one, but carbon-14 is isotope. And this was originally measured for like climate change stuff measurement, but thanks to the recent technology updates, according to them, they can measure 1 year resolution of the measurement with 1 year resolution. And then there are some sudden increase like this at 775 or 994, actually at least 8 events in recent 10,000 years. So the similar sudden increase observed in at least 8 events as of now. And almost simultaneously, and some barium and other ice core observations also showing some peaks almost same time. And of course, this is not only from one tree. For example, this year, I heard that 10 or 12 trees around the world also showing an increase together. So, and most possible cause of these increases are some strong particles from outside the Earth. And the solar event can be most candidate and most probable candidate. Because the 8 events, there are no 8 supernova remnants or gamma ray bursts. It's in probability. In terms of frequency, it's not possible. So, and we had an EC team 2 years ago. And for example, Hugh Harrison is here, and from Solar, and Ige Usoskin and Fusa Miyake from Japan, Ige Usoskin from Finland organized the EC meeting, and we had a review paper last year. And there are some vertical events happened, but the question is, is how large is it? How large X-cross flare? Actually, Carrington flare, it's too small. For now, too small to detect the carbon-14. There are still some discussion how large particles from Carrington event. There are some varieties. But the important point is how can we compare with stellar flare observations? But there are huge gap still. For example, in the right panel, this is a solar events for solar, as a function, x-axis is the cause X-ray flux of each solar flare, and y-axis is the particle event associated with each event, particle flux from Takahashi et al., Takahashi, Mizuno, Shibata paper. And yeah, please ignore this. The important point is even in the solar regime, particle flux has a very large scatter. And the particles associated with solar flares, sorry, I didn't explain, but maybe most of you know, high energy particles associated with the flares, but mostly with the solar CMEs, because as CME propagate into our Earth, in the shocks around at the CMEs, in my understanding, there are more experts here, maybe. But, there are some processes, and there some solar flares showing big CMEs, but some other not. So still there are big gap. So to the next step to compare flare frequency and particle flux, we have to fill in a gap, especially for the regimes and stars. Stellar CME, for example, stellar particle observation is very tough because the star is very far away. But next step, we have some stellar flare observation thanks to Kepler or TESS or other instrument, but we have to work on stellar CMEs for the next step. Okay. So it's a summary of actually introduction or part. So yeah, so from Kepler, superflares were detected even slowly rotating sun-like stars once every 1,000 years. And some unified picture like how star spots. Yeah, I can explain more on the statistical properties, but maybe please read my PhD thesis. But the important point is that there are still remaining important problems to be solved through multi-wavelength observations. I explained a lot of my talk. So especially how large stellar CMEs occur. So for the next step, stellar flares, we have some observations. Yeah, still there are many points. Yeah, for example, how emission happened in the case of stellar flares, stellar super flares. But stellar CMEs can be an important topic. Do you have any questions so far?
I mean, maybe you're going to talk about this, but is there reason to believe that they're going to scale in the same ways that when you get to, do they scale together so that when you get a super flare that's 100 times stronger, that you would expect to have a CME with its impact 100 times stronger?
I will explain.
Okay.
Let's keep going. Okay, maybe 2 pages later. Okay, and actually, why stellar CME is important? As I explained, of course, a connection to particles and flares, CME is an important part, but the stellar CME itself is also interested from the viewpoint of youngsters, actually. And one important point is it can affect the planets. For example, this is a picture from the Mars mission. But if CMEs, for example, can trigger a chemical reaction in planetary atmosphere, particles trigger chemical reaction, high energy particles, especially in young age, because if strong particles much higher than the current level trigger, the planet community is very interested in this topic recently. In addition, stellar evolution itself can be affected from stellar CMEs possibility. Because, for example, you may see a Austin Walk paper or Klammer 2017 paper. Young age, very young age, stellar mass loss or angular momentum loss also can be affected from stellar CMEs, not only winds, steady winds. So then stellar CMEs can be important. But yeah, actually, we go into your question. But what are likelihoods of CMEs with stellar flares? Given the known connections between solar flare energy and CME occurrence, we generally assume most large flares have CMEs, maybe, because at least large CMEs can happen with large flares, right? Maybe this is not the case, not always the case, even for solar flares. Yeah. Sometimes we want to extend the scaling, but is this correct? Maybe we have to think about more things. For example, people discussing the existence of large overlying magnetic field. This is very actively, still actively discussed. For example, sorry, I didn't explain, but most of the youngsters have a very strong magnetic field. So even in the case of the sun, maybe you remember 2017 September X-class X9 flare, or maybe if magnetic field is so strong, if the CMEs happened, but this can be suppressed. So with analogy of these solar events, several papers discuss the limits, there are possibly limits of magnetic field suppression, but observational constraints are very important. So we have to try to observe stellar CMEs. And actually, 5 years ago, I think when Jeff wrote the first edition of the textbook, stellar CME detection was much rarer than now. And still it's ongoing. But recent few years are great time. There are some candidates now, just candidates. Still, there are many discussions. I introduced some of the first, but this is a very hot topic. And we had IAU symposium, for example, in May, and there are some candidate discussions. But mostly, there are three approaches based on actually solar data. So three methods for the candidates with stellar CMEs in very recent few years. One is XUV dimming. This is, sorry for the tiny image, but if CME happens and high dense and hot plasma can disappear because it's ejected, the plasma can disappear. The disappearance of hot coronal component can cause a decrease of the EUV emission, especially EUV. Of course, it was originally found in Yoko X-ray. But for example, this is a light curve of the STSW light curve, flare happened, and after flare, CME occurred, and the EUV light is decreased for some time. And there are some candidates in X-ray observation still under debate because discussing quiescent component of X-ray is very tough. So, but Astrid Beroning paper and 2021 Nature Astronomy paper or other papers discuss the possibility of the dimming detections. It's in X-ray, so I think future EUV stellar observations are very important. But one example is X-ray dimming. And second, if plasma is ejected, there should be some Doppler shift of lines. And for now, actually, this is the topic I explain in the rest of my talk. Blue shift of lines, especially chromospheric lines like prominence, filament eruptions, blue shifts. I explain the next page. So I skip here. And third method is a radio burst. Plasma oscillation caused by CME propagation shocks. And I cannot attach the figure, but I remember in the conference in May, IU symposium, there was a report of type 2 burst detections associated, and they said they're preparing a paper. So some more radio candidates, especially low frequency and low far in measurement. And also there are some type 4 burst candidates, but still candidate or discussions now. But the radio bursts, maybe in a few years, there are more candidates, I think.
Yeah. There's the square kilometer array
Yes.
being built
Yes.
that almost certainly will nail that topic.
Yes, SKA, yes. So more candidates happened in the next 5 years, maybe. Okay. And I skip this. But today, with the rest of my talk, maybe next 20 minutes, I talk about our results. I introduce our results of the B, the blue shifts. And sorry, it's a very basic explanation. This is a presentation for stellar people. But in terms of mass ejection, there are several types of the forms, and our observation is, I talked about stellar CMEs, but our observation, filament and prominence eruptions. Filament eruptions, it's cool plasma, core of the CMEs, cool part, and low temperature part. And if on the disk filament eruptions, and if on the And out of the disk, it's observed like prominence eruptions. I think this is I heard this observation is from Colorado. I heard in I forgot in near Kappa Mountain.
Climax, the
Yeah,
original HAO,
climax, yeah. And so HAO, original station of HAO. Yeah, okay. So today I briefly introduced the two results. And we worked on G dwarfs, sun-like stars, young sun-like stars, and M dwarfs. And especially focus on these two papers. One paper from Nature Astronomy 2022 by Namekata-san, led by Namekata-san, our collaborator, and one paper I published recently on M dwarfs. So we had a press release on G dwarfs thing, so you may read if you're interested. So we observed, and for this observation, Kepler surveyed a lot of stars to detect flares statistically, but we want to investigate one event more detail. So for this case, we focused on a very young solar analog star, so the young sun-like star, EK Draconis, and age around 100 mega year, and one of the most nearby active solar type star. And the super flare is 100 times larger than the current event occur once in 10 days. And 2020, actually this was during COVID time, so the observation was very tough, but they made it, Japanese collaborated, made it. We had observation for TESS photometry. TESS is similar to Kepler. It's a space telescope observing white light. And H-alpha spectroscopy used two telescopes in Japan. And for more than 2 weeks monitoring. So every day they observe this star for 8 hours every day for 2 weeks. And finally we detected one event. So it was tough observation. But in TESS, like Kepler, we detected a flare here. It's not big flare, mixed super flare, but still super flares, larger than current event, 10 to 33 L. And here, and in H-alpha, we detected a flare. Same. This is the difference H-alpha equivalent with us. So there are some increase, but after that, after the flare, H-alpha showing a decrease like this, and it decreased 2 hours, and fainter than pre-flare phase. So some absorption could happen. What was that? And if we saw the spectra, we can know the answer. So the middle and left panel is the same light curve of the H-alpha difference equivalent with us, but it's difference from quiescent phase. Quiescent phase is subtracted. And the middle panel is the H-alpha difference spectra. So the quiescent spectra is subtracted. Only the difference from the pre-flare phase was plotted. And as you can see, during flare phase, H-alpha is showing this almost symmetric emission. But in a later phase, there are some blue shifts like this. So these blue shift absorption can be explained if cool plasma is moving products and absorb the light and flare emission. So this can be a first detection of a possible mass ejection, especially filament eruption or G-dwarf stars. And we detected similar events. Also, actually, this event was detected with 2 telescopes. So this was a real event. So this was the first possible mass ejection of solar type stars. And
Question.
Yep.
Is the velocity at the blue shifted absorption maximum exceed the escape velocity from the star?
It's still a bit smaller. And actually, I have a slide a few bit later, so I explain. And this is a very important question, actually. Thank you. So this is a G-dwarf detection, but we had I skipped this. We also try similar things to M dwarfs because G-dwarfs, yeah, it's still active. G-dwarf is very important, but recent exoplanet community had interest in M dwarfs. Also, M dwarfs more frequent flares than G dwarfs. So G dwarfs, even young G dwarfs flare like every 10 days, but M dwarfs flares every day. So if you observe the M dwarfs with spectroscopy, young M dwarfs, I mean, and if you don't detect a flare, you are very unlucky. So actually, we did try some very young M dwarfs similar type of observation, but US telescopes and some photometry and even X-rays. And 41 flares with from starting one night, so every night flares. Because why MDOS? Because we want to know some statistical properties by detecting more flares. And and among them, we detected 7 bluing asymmetry, I mean blue shifts of the line profiles. MDOS, it's, sorry, I skipped this slide, but MDOS, flare an H alpha line profile already emission. This is different from before flare because photosphere is very faint than GDOS. The sun, H alpha is absorption only, and if flare lines are a bit shallower. But MDOS is already emission, but if flare happened in some increase of that emission line. Okay. And this is a left, sorry for busy figure, but I showed one example. So this is HR4 and H beta line intensity light curve as a function of time. The x-axis is hour and the y-axis is line intensity or equivalent with this. And as you can see, there are, yes, a lot of modulations, even one night. But this is here. So there is a very long time scale flare for 4 hours, like here. And the interesting is there are almost nothing in optical, so only in H alpha, or actually X-ray has some response here. So X-ray H alpha, it's very soft flare, but no white light emissions. Yeah, possibly some in increase here, but we don't know. And the interesting point is if we see the line profile here or here, and this is a different line profile because quiescent component is already subtracted. But the line wing of H alpha is more enhanced than red wing. So this called blue asymmetry. Blue wing is enhanced during flares. And this is a difference profile, quiescent component subtracted. And we can see the time evolution of these line profiles like this. So this is a complicated figure, but the y-axis is the time here, same hours. Time. Oh, sorry, I forgot to change the in English, but it's hour. And x-axis is the wavelength or velocity. And around these here or here, number 5 or number 3, there are blue shifts, blue wing enhancement component, but other part nothing. So there are some short time scale asymmetries and around here. So this is one example of the MDOS. Or there are another example. This is also non-white light flare, but there are some dramatic line profile shifts during flares, during a flare. So this is a H alpha H beta increase for. Also, this is a very long flare because flare is so big for MDOS. MDOS is fainter. It's still actually comparable to X-class flare, but the MDOS is so small. So for the star, it's so huge. And if we see the line profile around here, yeah, blue asymmetry again, or blue wing is enhanced. So some plasma is moving away, maybe. But now later phase, red part is more enhanced. So the plasma is moved far away from us, maybe toward the star. So some shifts from blue to red in the same color map, profile intensity map. So some area phase, blue asymmetry and red asymmetry. And also blue asymmetry is very long, like few hours. So then these results suggest that the situation is not so simple. So sometimes the blue wing enhancement suddenly appear and decrease, but some cases much longer phase. So summarizing the results, I don't have a time to show 7 events, but if you're interested, you can see the paper. There are some variety of asymmetry, 20 minutes, the sudden appearance, or much longer time scale asymmetries, and maybe both and non-white light flares. So yeah, and even other lines sometimes showing the asymmetries. So this may be constraints on cool plasma temperatures maybe. And what the cause of the asymmetries? There are two main possibilities. But sometimes cool upflows from flaring chromosphere can show blue shifts, even in the case of solar flares. It's called blue asymmetry. But the velocity is usually smaller than 100 kilometers per second for example, in H alpha. So we assume, and the most probable candidate is cool mass ejection, prominence of filament reaction. And even in the case of in the case of M-DOFs, even filament eruption, the plasma on the disk can be observed in emission, according to the calculation by this paper, because photosphere is fainter. So from here, of course, we still have a compare with the modeling, but this will be the next task. Sorry, we cannot say the clear answer, which was the cause of the M-DOF asymmetries. But we assume, and from here, we assume these caused by cool mass ejections, and discuss how velocity is and how large mass ejections are. So for quantitative discussions, we did a very simple fitting, and assuming that just subtracting a symmetric component, and we fit the Gaussian fitting to excess component. And then assuming H alpha intensity with, assuming the relation between H alpha intensity and mass, because we know the H alpha integrated intensity with solar prominence. In the case of solar prominence reaction, there are some relations, and based on Heinzelt 1994. Yeah, of course, we have to do M-DOF calculation in the next step. But we can discuss how large mass can be ejected associated with each flare, and we can compare with stellar data. And this is the results. Well, this is a busy map, but I explain. So first, y-axis is the mass, ejected mass for each event, and x-axis is the total bolometric flare energy for each event. And gray X marks, these are solar CMAs from GOES X-ray and LASCO image from Gopal-Swamy or Yashiro and Gopal-Swamy. Sorry, I forgot which one, but Gopal-Swamy, no, Yashiro and Gopal-Swamy 2009. And these pink points stars are solar filament eruptions from H alpha observation, H alpha velocity observations actually. It's very rare. And the red points are M-DOF events, and also G-DOF events are introduced in earlier part, also plotted here. So the stellar, for the mass, stellar events located here, and some actually binary events also, but it's not G-DOF and M-DOFs. So there's some stellar events, most of the stellar events located here. So the estimated mass is comparable to expectations from the empirical relation between flare energy of mass and solar CMAs. So this may suggest a physical similarity between solar CMAs and the M-DOF or G-DOF mass ejections. But how about velocity? And velocity might be a bit different. So yeah, we have a mass and we have a velocity. So we can discuss the kinetic energy of the events. And okay, we plotted the events. Solar field is here, or M-DOF is here. One or two order of magnitude smaller than solar radiation. And our immediate impression is the CMA suppression. The kinetic energy is smaller, but mass is same. So mass is consistent, but kinetic energy is smaller. Maybe velocity is smaller, but we have to be careful. Yeah, and actually, most of the events is smaller than escape velocity, according and. Jeff, maybe these are smaller than escape velocity actually.
By a big factor.
Yeah, but
If you compare 100 kilometers a second.
yeah.
Escape velocity of what, 600?
Yes,
600? Yeah, 600
for G-DOF and M-DOF a bit small.
maybe more.
Yeah. 600, yeah. But yeah, 600, I think. But we have to think about is that in H alpha we observe the prominence eruptions, but these gray points are CMAs, and CMA is much faster than prominence eruption, filament eruption, because plasma is gradually accelerated once H alpha is ejected, but prominence eruption is ejected. It's gradually accelerated into a CMA speed. And for example, like this. Or if we compare CME speed and prominence eruption from Kopasu-Omi 2003, so the velocity difference exists. So more investigations are necessary. So we only observed a very early phase of the whole eruption. H alpha is only the beginning phase. So we have to observe the later phase, or we have to investigate more later phase. So the next step, comparisons between other methods are very important. For example, so the first second point. First, we need more X-rays or even radio observation simultaneously with H alpha, because H alpha is the early phase. And other methods like XCB dimming or XCB line velocity measurement or maybe radio observations is more sensitive to later phase coronal event. So future observations are very important. I explain the future mission plan after maybe last few minutes. Also, this is just ejection observations, but we are working on some simultaneous magnetic field characterization with Zeeman Doppler imaging. Actually, we are just working on these new observations with magnetic field observation to compare with an eruption modeling. Now, actually, for this, solar-based modeling is very important. For example, how stellar CMEs can propagate or eject if under the condition of magnetic field, or how stellar prominence should be observed. We just started the discussion, but for example, the velocity measurement, I assume the solar relation, but the MDOS may be different. Maybe some other factors. So more modeling studies based on solar knowledge is very, very important. Okay, so this is a mid-summary, almost a summary. So we detected some blue shifted events in GDOFs and MDOS, and there are some candidates, and there are some physical similarities, especially for mass. But from velocity observations, we need a more future investigation, especially comparing between other methods. For example, how magnetic field can affect mass ejection in the case of stars, or how XUV stellar CME candidates can relate with H alpha measurement. Unfortunately, so far, all the measurements are done separately, but we have to observe the same event with different wavelengths. And of course, solar-based modeling is very, very important. Now, yeah, we are now working on some, now some projects with many collaborators. For example, we work on some projects with Rachel Sten or Adam Korski or students on MDOF, more observations. For GDOFs, we work on some more international collaborations. Even using Hubble, we did some observations in earlier this year, GDOF again. So next few years, please. More collaboration also important, and I can maybe introduce next year or a few years. I can introduce more results. So please wait. Let's get this right. Oh, and I think Cole can present in the next time, but even solar flare observation can help. I briefly mentioned even not only prominence eruption, sorry for complicated stuff, but the line profile has solar flare line profile measurements are still important because so our group also working on how line profile asymmetry can happen with flare emission, not only from prominence eruption, but through decast, high resolution observation, how each component can contribute to line emission before understanding stellar line profile asymmetries. Maybe I don't have a time to detail, so I keep this. The future, so I think I finish in 1 or 2 minutes. Future, the last has a 2 mission plan. Actually, one is already fixed. I'm a member of ESCAPE, by the way. Now, one is, sorry, I explained an ESCAPE mission. I think I mentioned EUV dimming is important in the case of stellar CME observation, but unfortunately, so far, there are no EUV. There was a EUV instrument almost 25 years ago, in the 1990s.
EUVE.
Yes. But this was not sensitive to detect dimming. This detected EUV flares, but its sensitivity was not enough to detect dimming. But we proposed. Actually, we tried to propose again for astrophysics proposal call, almost just open. It will be deadlines early next year. we tried to meet astrophysics MIDEX again. Actually, this was selected phase A, but failed at the final point. But we try again. But this is ESCAPE mission led by Kevin France. I think Jeff was a member of the last proposal. Right?
Escape.
Yes. And this is EUV and far UV spectroscopy and 50 times EUV sensitivity than previous EUV measurement 25 years, more than 25 years ago, trying to detect CME frequency distribution via coronal dimming or CME kinetic energy for brighter stars. So EUV dimming observation we try, but of course it's important to compare with the solar counterparts or HRF or other observations. And this is EUV dimming observation, but we also have already last team, especially Brianna, she is a very young researcher in last, already accepted CubeSat mission for EUV flares. It's not for dimming. The CubeSat is not sensitive to detect dimming, but EUV flare observation will happen for some stars, some brighter stars, launched 26 or 27. This will be so it's still a UV observations. There are more opportunities, and also Kevin and I also starting to collaborate with Japanese team. They provide a far UV spectroscopy. It's very similar to Hubble Space Telescope. Sensitivity is also similar, but this was more stellar observation time, and it's still mission candidates, selected candidates, still like a phase A. But yeah, not only ESCAPE for US missions, there in the worldwide, there are some UV observations to detect CMEs or flare emissions in the next step. And the collaboration with the solar is very important. So in summary, so the first step was the whole research was started from Kepler discovery of superflares, but now in the next step, now we are in next step to trying to detect the stellar CMEs. Still, they are candidates because we don't know all of the events correspond to CMEs or some of the flare line profile emission. So we have plenty of things to consider, but for this comparison among different methods, new UV, of course, new astrophysics UV observation, but also solar collaboration with solar missions or solar UV knowledge is very important. Well, modeling is very important. So that's all for today's presentation.
Thank you. Questions?
Yeah, maybe many questions during the talk. Oh, yeah.
I have a question. Yeah, so very interesting stuff. And when you were looking at can you go back to the plot where you showed, I mean, you got right down to the question I was asking about the relationship of the CME and the flares. Can you go back to the plot where it showed the kinetic energy?
Oh, yeah.
And you were saying there are various uncertainties there. One of them being, that you're comparing white light CME velocity after the acceleration when it's kind of reached its maximum velocity versus something which might be while it's still accelerating. Has anybody ever made that plot but using filament eruptions velocities close to the sun? And a related question to that,
These pinpoints.
which ones? But there's many more points. Those pink. What are those pink points?
Actually, this is only from smart observations. Smart HFO
Doppler
shift in Japan.
Exactly. So it's very rare.
Yes.
Whereas the gray ones from the CMEs are probably using white light or something like that. So you could make a plot. You could make a plot using the H alpha, or just the prominence. I've seen plots where you look at the acceleration, where you've got measurements of velocities of prominences down low, and so not using Doppler, but using just the tracking time height.
Yeah, that could be possibility. Yes. Yeah, and actually, there are some possibly other point, but I discussed with I think Katie and so Kevin Reardon about MCCD measurements. It's in there are some very old HFR measurement not yet analyzed in terms of this point, so we may increase the number of points of HFR.
Yeah, and close and related to that, do you have a sense of how close these measurements are to the star?
For stellar events.
For the stellar events. Do they have to be seen in projection on the stellar disk? The light, I mean, once they move out far enough, they're gonna,
Yeah, we have to think about projections. Yes,
okay, so they're probably pretty close, right?
yes, yes.
So you probably could get a sense of, I don't know if there's any way to know how close.
Maybe like a 10%, 20% of stellar radius. Sorry, I forgot the exact value, but actually in one GDOF event recently, we tried to discuss that point. Because the GDOFs and if GDOFs, if the one event, we just published the event, I can show you the paper later, but GDOFs, if the event is on the disk, it observes a filament eruption, but it's out of the disk, it can be observed as from an emission. And using that knowledge, we try to constraints. It's still very rough constraint, but yeah, we can discuss.
That's very interesting.
Yeah.
Anyone? I have a question.
Yep.
Oh, go ahead.
Yeah.
Earlier, you showed these power laws derived for different solar-like stars weighted by rotation rate. So one thing which came also out of the Kepler study is, I mean, also work Travis Metcalf and collaborators talked about that the sun seems to be in some transitional regime that's not anymore in the Skomanich law efficient braking. So it has a more wimpy dynamo. So that brings me to the question, those stars in this red one, where the solar rotation rate in there, are any of those in this transitional phase, or are all of them still pretty much in the strong braking regime?
I think almost all the stars are before the
Yeah.
braking change.
Yeah. So there is a possibility that maybe super flares on the sun are less likely because the solar dynamo does some transition where it gets more wimpy than
Yeah,
the
maybe
dynamos you may find on those
more
stars.
super flares after that point.
Yeah.
Yeah, that would be another interesting topic. And actually, rotational evolution is actually, this is very interesting point. Rotational evolution is very interesting results recently. I think you can hear Travis Metcalf talk somewhere. But G-dwarf rotation evolution. Also M-dwarf and K-dwarf has also interesting rotation evolution. The activity is much longer, for example, M-dwarfs than sun. So even M-dwarfs older than the sun can generate super. Proxima Centauri is the example. So and such long-term evolution of flares are very important because if we think about the effects on planets, effects can be like cumulative effects. That rotation evolution is very important, I think. Yep.
Yeah. To add to that point, CMEs, of course, are directional. So the effect on the planet is only when the CME is headed towards the direction of the planet. But M dwarfs have planets that are very close in,
Yes, yeah.
especially in the so-called habitable zone, liquid water. So close-in planets are much bigger targets for CMEs to hit than, say, the Earth around the sun. So it's a much amplification factor. My guess is that essentially all M dwarfs, exoplanets in the habitable zone will be just bare rock, and CMEs have done the thing of removing the atmosphere. Okay, the other thing I'm going to get your opinion on. Several years ago, various people, Jeremy Drake, I think is one, and Arnaud is another, pointed out that if you take the power law from solar CMEs of the mass versus energy and extrapolate it up to the energy of these super flares, what you find is the energy exceeds that of the total luminosity of the star. And if you do the similar extrapolation of kinetic energy, you get enormous numbers, which is why Alvarado Gomez made the argument, a very strong argument, that magnetic fields suppress CMEs. So you don't get into this point where the CME mass loss, is enormous. So but that was several years ago. So what's your thoughts on this today?
Yeah, actually, there are great discussions, including I think all of these researchers in Coulter's session, and his paper. Yes, some weaker events can be suppressed, but after the start, if flare is enough big enough, the magnetic suppression can be overcome magnetic suppression. Ejection can overcome magnetic suppression, but
Even for multi-kilogauss magnetic fields. I mean, some of these M dwarfs have
yeah,
like
Yeah.
4, 5, 6 kilogauss magnetic fields.
that's right.
So I think,
Yeah.
agree, this is a matter for more discussion.
Yes, I think
Yeah, I
observation.
just want to know your opinion today on this.
Yeah, actually, the immediate answer is I think observational constraints are very important. So we try to observe the mass ejection and CDI together simultaneously because the magnetic field can also time changes, time evolutions, and yes, I think I don't have a final answer yet.
Yeah.
Sorry for
Well, another aspect of the problem, which is really very concerning, is I've seen estimates of the production of NO and NO2 from CME events.
yeah.
Okay, and NO and NO2 can easily suppress ozone.
Mhm.
So that's a way of sterilizing a planet's surface, eliminating the ozone. And apparently, at least the calculations I've seen, the amount of NOx is what it's called, sits around for 100 years. So you destroy ozone for 100 years and think about the effects on biosphere,
Yes.
surface of planets.
I think I remember this paper is discussing the possibility of the ozone depletion
Yeah.
caused by strong high energy protons caused by
Right.
CMEs. And if one superflare can happen, I think this paper suggests one event can decrease the ozone for 2 years.
Yeah,
90
but
years.
multiple events
yes,
decrease it forever.
yes. So this can permanently change the chemical, especially ozone situation. And some exoplanet researchers trying to detect ozone as a biosignature of oxygen, but if younger stars, ozone can destroy it. So for discussion of the exoplanetary atmosphere chemical reactions, yes, ozone is a good example to think about CME effect.
Mhm.
I completely agree. Thank you.
Okay.
Yeah, I wanted to come back to these events in actually not too far back times where there were these changes in carbon-14
Mhm.
and beryllium in very short time scales and much steeper than the regular
Yes.
changes with the solar cycle.
I think these changes roughly corresponding to not 11 year, but a longer time scale for activity changes.
Well, but my interest is, I mean, obviously those were drastic events.
Mhm.
They hadn't any significant effect on the biosphere or on people. Otherwise, we would have heard about it. But in today's world, with all the technology around, that would be not good.
Yes.
That would be a real disaster.
Probably, maybe these treating events a bit smaller than the superflares with Kepler, but still larger than Carrington event. So maybe 10 to 33 L.
Yeah.
I think I'm a bit conservative. Maybe not 10,034 L, but 10 to 33 L. So it's still 10 times larger than Carrington event, or at least 5 times larger than the Carrington event. It's like a disaster. These results suggest yeah, such event can happen 1,000 time scale. But so then we need more studies and for how the real event was. Yeah, from space weather point of view. Yeah.
Another question.
Oh, yeah.
I have a quick question. Back to M-DOR.
Mhm.
What would be your speculation about M-DOR flaring every day?
Flaring it.
You said M-DORs flare almost every day.
Oh yeah. We have what is speculation?
What is why? I mean,
Okay, sorry. I mean, no. We had a. Sorry, I didn't show the example of the right. I had a figure, I think. Oh yeah. Sorry, I skipped this presentation. But this is a Kepler like observation of one M-DOR, very young M-DOR. Actually, we observed this for CME observation. You can see there are so many spikes here in all of flares. So these kind of test data, we have a flare frequency distribution from stellar data, and we discuss every day. Every day is just a rough scale. Of course, we can discuss a more exact number. But young star.
okay.
Yes, check this.
And
Oh yeah.
So if on the y-axis, you do have the normalized flux.
Yeah.
And so the flux means that okay, we're luminosity on the star itself, and if you have more magnetic field installed, then you will have less flux, right?
Yes. So
So-
these are stars for moderation, but on average,
I'm just asking a very generic thing, like okay, like I don't know much about it. So basically, if you have bigger sunspots, less light,
oh yeah, that point is
and if you have a smaller sunspot, that means you will have more light.
yes.
So in that case, most of your flare peaks are coming where there is a peak in the flux itself. That means there's less magnetic field and more flares.
This is an actually interesting point and important point. Actually, maybe star spot, not one star spot, and one dominant. Yeah, there are still debate how the magnetic field or sun star spot is located on the surface, because our current naive understanding is there are many spots there, and one dominant spot generate dominant light curve changes. But of course, these flares caused by the small spots located the other side of the big spots can cause these super flares, or inclination angle also affecting.
And again, like these intensity flux, if they are showing the magnetic field,
Yeah.
they're very much periodic, like, and on the scales of like a few days, right? So like how those stars are like having, because like generally on sun, it's not the case. Like,
But the star was born with such fast rotation. Even our sun has a rapid rotation like this, few days, but it's spin down as a function of angular momentum loss.
yeah, but still like you don't always have the same number of sunspots which will be coming every month. So that will be always be having some sort of changes.
Yeah, almost always. But amplitude, if we observe the star again in the next year, the amplitude may change a bit. So some activity cycle also, but this also our limited observation time. Our knowledge for long-term changes are very limited. But this is a very another hot topic. Yes.
Yeah.
Yep.
Anyway, along the same point, the fact that there's an up-down motion periodic means the spot distribution is anisotropic.
Yeah.
If it were homogeneously distributed across the star or only at the rotational pole, you would see no up-down motion. Okay. So the question I have is, anybody ever looked at whether the probability, looking at a lot of data of these big super flares, is mostly at minimum or maximum or somewhere in between?
For this light curve, actually, we did it, and we are writing another paper. But for most of the events, no difference, like no significant difference. Yeah, flare can occur in all rotational phases. For this at least.
Okay.
Yeah. So it's Interesting questions, but maybe multiple spots and maybe dominant large star spots cannot be related with star spots.
Well, anyway, you have to have a dominant spot, a spottiness.
Yeah, spots, sorry.
In order to see the periodic motion. And if it's not, and if the superflares are not correlated with the light curve.
Yeah.
That says that the flares can occur on small spots,
Yeah.
not always associated with the most dominant regional spots.
Yeah. This can be also related with flux emergence, maybe. The flare can have, even in the case of the sun, flare doesn't occur on the spot, right?
No, it's
Yeah,
nearby.
around the edge, like between the spot. Yeah, maybe, but that will be another step. And maybe multi-wavelength observation may help, like how UV quiescent UV light or HK, HF changes with this kind of modulation, for example. Any question from online?
I have a question.
Oh, yeah.
So how does the size of the spot compare on these like smaller stars compared to the size of the star? How?
Oh, yeah. Like a few tens of percent. Like 20% of the stellar surface. Yeah.
So I'm talking about, let's say, one spot, like one big spot.
Oh. Yeah, one big spot is like this size. Yes.
Okay.
Yeah. We can. I don't know. The word spot is correct or not. It's
Maybe spot group.
yes, group. Yeah.
And again, like from these light curves, how we differentiate if you're looking at a star spot or a planet? Because like the planetary detection kind of
The planet is more like periodic.
yeah.
Still, the star spot, the amplitude can change, and there are some certain size. Planet is very small, so only because the planet transit can happen very periodic with the very determined periodicity. So if we have use a Fourier analysis, we can distinguish very
Okay.
easily. Any questions? Yeah, thank you for many questions. Any question online? Well, if you have any more questions, please email me or tell me, or I will hear again in 2 weeks for Boulder Solar Day. So you can chat, or I can available like next 1 hour or two. So. Thank you very much.
Okay,
Thank you.
Yeah,
thank you.
yeah, thank you for many questions.
Excellent job.
Stop sharing. Can I? Oh.